Hello, everyone. Welcome to the colloquium at TIFR CAM. Today, we have the pleasure of having Professor Andrea Malchiodi from SNS PISA, and he'll be telling us about a variational approach to Liouville equations. Over to you.
Okay, thanks for the introduction and especially for the invitation to give this talk. So it's really a pleasure for me. Okay, so let me recall some basic facts about the role of Liouville equations in conformal geometry. So I start from a really simple setting of a closed surface, two-dimensional, no boundary, with a metric G. And I consider now a conformal change of metric. So G is the initial metric, and now I want to deform it conformally, which means that for every point, I scale the metric by a positive factor, which I write in this form. And then I observe how the Gaussian curvature transforms when I conformally change the metric. So kappa G is the background Gaussian curvature, and kappa G tilde is the Gaussian curvature of the new conformal metric. And they are related by this formula, which is a Liouville type equation. So a classical problem is the uniformization problem for more than a century ago, which consists in trying to find the conformal metric on a given surface with constant Gaussian curvature. So it means that by this transformational law, you need to solve for this PDE with here kappa G theta equal to a constant that I call K bar. Okay, so that's the equation you need to solve. If you're able to do it, then you uniformize the surface. And there's a constraint on kappa bar. So by the Gauss-Bonnet theorem, it should be given by the integral of the background Gaussian curvature with respect to the original metric. Okay, so let me present a PDE proof. So the classical proofs are back to Koebe and Poincaré. So the problem was posed by Klein, but there are more modern proofs which exploit the variational structure of the equation. Okay, first of all, locally, there is a standard way to solve for Liouville equations, and this can be done by complex analysis. So you consider meromorphic functions with simple poles and with f prime different from 0. And then locally, using this formula, you can find solutions to the Liouville equation. But the problem is to somehow to patch such solutions on a whole surface. Okay, so you can use some PDEs, but as we will see at the very end, you would also need some geometric insight to resolve mostly compactness problem. Okay, so there's an easiest case in which the constant K bar is 0. So by Gauss-Bonnet, we are on a torus, and the equation simply becomes this one. So let me go back to the original equation here. Okay, when we solve for K bar equal to 0, then we just have a linear equation. Okay. And the condition to solve for such an equation is that the right-hand side should integrate to 0. But that is true because of the Gauss-Bonnet theorem. Okay, so we are in the torus topology, and you can exactly solve for this equation. So this was the easiest case. Let me now present the variational structure of the equation. So solutions are extremals of an energy which is defined on the functional space W12 of sigma. So W12 is the space of functions which are of class L2 and with also gradients in L2. And formally, solutions of the above equations are critical points of this function. Okay, so by Gauss-Bonnet, I can assume that the constant K bar in the right-hand side of the equation is the integral of the Gaussian curvature of the surface. And this makes the energy invariant if you add the constants to U. So this reflects somehow the geometric invariance by dilation of the problem. This energy has also an interest in string theory or in spectral theory through the formula by Polyakov in string theory. And there are also applications to spectral theory by Osgood, Phillips, and Sarnak. So it was used in particular to study compactness of isospectral metrics on a given surface. So with respect to the CK topology. And the problem is actually much less understood in high dimensions. So there is some study with respect to some given maybe conformal class in dimension 3, but that's basically it. So it's pretty much open and very interesting. Okay, so how do you find then the critical points of this energy? So a fundamental tool is the Moser-Tudinger inequality, which I will briefly recall. Okay, so first of all, let me try to simplify a bit this energy. So I use the Poincaré inequality, and for the Poincaré inequality, this linear term is sort of lower order compared to this one. So I can basically replace U by the average in this formula, and then you get to this simplified expression. Okay, now, if you are in 2 dimensions, the space W12, so which means, I repeat, functions with gradient in L2, embeds into any LP, but you can push the embedding to exponential class by the so-called Moser-Tudinger inequality. So there is also some previous work by Pojaev, but most people still call it the Moser-Tudinger inequality. And this allows to estimate the log of the integral of the exponential of U. So once you subtract the average to make it invariant, so U bar is the average in this formula. So the log can be controlled by a constant 1/4 pi times the Dirichlet energy. So namely the integral of the gradient squared. And this shows that if K bar is negative, then actually, for any K bar, the functional, this functional is bound below on W12. By the way, on the round sphere, there is a sharp inequality. You can take this extra constant, which in general depends on the surface and on the metric. So for the round sphere, this constant is equal to 0. So that is known as the Onofre inequality. But what I will care mostly about is the multiplicative constant here. So this will be less important for me. Okay, so let me consider now the case of K bar negative. In this case, the energy becomes coercive, so which means that it tends to infinity when the norm tends to infinity. And therefore, in such a case, it is very easy to find the global minimum by the direct methods of the calculus of variations, which is also unique. And therefore, you can easily solve for the problem if also K is negative. So we saw the case K equal to 0 before, the easiest case, and then K bar negative is the next case in order of difficulty. What is difficult is the case of K bar positive. So we are now by Gauss-Bonnet in the spherical topology. By the Moser-Tudinger inequality, the energy is bounded below, but that doesn't mean that you can find minima, because you might imagine just a function or in R, already in R, which is bounded below, but which has no global minimum. So you might have things like asymptotes. Okay, and this actually corresponds to some analytical difficulty, to a loss of compactness phenomenon. So in this simple case, you see that minimizing sequences tend to escape to infinity. Okay, so you lose compactness, and the same happens here. So what causes trouble is the family of Möbius maps, which are conformal maps from S2 to itself. And they act on conformal factors in this way. So don't look at the formula, don't look at it too much. But if you start from a conformal factor W, then there is a natural transformation in it, a sort of action which is induced by a Möbius map in this form. Okay, so what is the effect? So don't look at the formula, but if you start from a conformal factor, which is essentially bounded at the beginning, and then you apply a Möbius map, so what you see is that the new conformal factor would tend to concentrate at a single point in the form of a Dirac measure. So this is a loss of compactness because so while somehow the measure stay bounded, but then the weak limit is 0. Okay, and so you lose compactness in this way. Okay, so when this happens, the energy stays bounded. And how can you recover compactness? So here comes some geometric insights. And I want to present a proof due to Ding from the 90s. Okay, so fix a point P on the surface and consider the following equation. So I'm replacing the right-hand side, which had an exponential function, by now a measure, which is the most concentrated measure you can imagine, namely a Dirac delta on the right-hand side here. Okay, now the solution that you can find is actually as singular as the two-dimensional Green's function. So it has a logarithmic singularity at this point P. And if you look at the problem geometrically, so away from the point P, the right-hand side is 0. So which means that if you consider the surface with the point P removed and with this conformal factor, the right-hand side is 0, which means that the Gaussian curvature of this conformal metric is 0 by the transformation law we saw before. Okay, now recall that we're dealing with a surface with the topology of the sphere. So now, if you remove a point, it's a sphere minus a point. So it's a set which is simply connected. By the asymptotics of this singular function, you get a complete metric and with 0 Gaussian curvature. Now there is a classical theorem in geometry that tells you that such a surface with this metric must be isometric to the Euclidean plane. Okay, and now once you have the isometry to the plane, you can compose with the inverse stereographic projection to get a sphere. Okay, so that's how you can solve for the uniformization problem with the PD approach. And now, while in the case of negative curvature, the solutions were unique, now they're no more unique because you can compose every solution with a Möbius map. So you get as many solutions as Möbius maps. Okay, so recall that the energy functional that I used before had the following approximate form. So you have the Dirichlet energy and then some coefficient which multiplies the logarithm of an exponential. Okay, so pretend, so we know that in 2 dimensions by Gauss-Bonnet, the integral of k is always less or equal than 4 pi, so which is the value on the sphere. But pretend for a moment that it would be bigger. Okay, so that would imply that this energy would become unbounded from below. And then to control this term by means of the Dirichlet energy, you will need a sort of improved version of the Moser-Trödinger inequality. Because the Moser-Trödinger inequality was allowing you to control this logarithmic term by this one exactly with a factor of 4 pi. Okay, but if this were bigger than 4 pi, you will need some improved version of the Moser-Trödinger inequality. Okay, so they're not true in general because the constant in the Moser-Trödinger inequality, 4 pi, is sharp. Okay, but it turns out that for some functions you get an improved inequality. So let me show some examples. A classical one is by Moser in 1973. So he considered functions on the sphere which are antipodally symmetric. Okay, so embed your sphere in R3 and you require that u of x is equal to u of minus x. Then in this case, you have a Moser-Trödinger inequality, but with an improved factor. So you have 1 over 8 pi instead of 1 over 4 pi. So which means that you are able to reduce the multiplying constant by a factor 1/2. There's another example by Aubin, which does not require this antipodal symmetry, which is a very strong requirement. So he proved the following: embed your S2 into R3, and you consider functions that are balanced. So namely, the center of mass on the sphere is at the origin of R3. Okay, so the volume is sort of equidistributed on the sphere. Then you can still get this improved inequality. This improved inequality actually holds even with C equal to 0, as it was proved by Gui and Moradi-Pham a few years ago, with a very nice, say, geometric argument. Okay, so as I said, this improvement holds in special situations. It's false in general, but it tells you actually some consequence. Okay, so for example, if you don't have the improvement of the inequality, if you are on the sphere, then it means that the volume must be unbalanced. Okay, so the center of mass is no more at the origin, so it must be somewhere here, and therefore the function center of mass is avoiding the origin of R3. And that's information, so it tells you that there is a sort of hole in the image of this center of mass map. And well, once you create a hole, you're creating some topology. And the topology can be exploited via sort of variational or most theoretical arguments to find sometimes existence of critical points. Okay, let me also mention that more recently, there was a yet improved inequality by Chang and Heng, assuming orthogonality of the exponential function to more spherical harmonics. Okay, so center of mass 0 at the origin means that the integral of e to the 2u times the Euclidean coordinates is equal to 0 for any I. Okay, so this means that the exponential function has a zero product with the first spherical harmonics. And Chang and Heng proved that if you have orthogonality to more spherical harmonics, then you get a yet improved inequality. Okay, so I was pretending that the Gauss-Bonnet integral were large. This doesn't occur for the Gaussian curvature, but it occurs in other Liouville type problems of variational type. So let me mention some of them. So one example is the Q curvature in 4 dimensions, which is a natural counterpart of the Gaussian curvature. So you have a nice conformal transformation law. There is yet a Gauss-Bonnet integral, which involves the Ricci tensor and the Weil curvature. And in those cases, it can exceed the one of the sphere. So this curvature doesn't control the full curvature tensor, as in 2 dimensions, but still you can get some useful geometric conclusion. So I mentioned works, for example, by Gursky, Chang, Gursky, Yang, Pfefferman and Graham, and others. And the analytic study of this Q curvature equation is also quite challenging. And you get interesting phenomena of blow-up, for example, as shown by Adimuthi, Roberto, and Struve, or also by Hader and Martinazzi. So there is a much wider variety of solutions. Another example, which is a one I will discuss today, is that of conical surfaces. So I will get there shortly. And there are also motivations from mathematical physics, because the Liouville equations describe mean field models in stationary flows in dynamics, electroweak theory, and Chern-Simons models in superconductivity. So these are, for example, some references, and you can look, for example, at the books, the very nice books by Isong Yang and Tarantel. Okay, so now I want to turn to conical surfaces and the role of Liouville equations there. So the prototypes are polytopes, which can be obtained locally just by folding a planar conical sector. Okay, so you take this conical sector in the plane, And then you can decide to fold it, for example, according to these angles. And the total sum of the angles in this case is not 2 pi, but it's less than 2 pi. Okay, if you look at the Gaussian curvature, well, it will be actually 0 where here you're bending the paper, okay, because still it's a nice isometry. So if you have an isometry, you don't change the Gaussian curvature. It's a classical theorem by Riemann. But at the conical tips, because of this discrepancy in the angle, the Gaussian curvature has the shape of a measure which is supported at the vertices. So there is no Gaussian curvature on the edges, but instead there is Gaussian curvature in the sum of Dirac deltas at the vertices of a polytope. Okay, there's a classical theorem by Alexandrov from the 40s saying that any topological sphere for which you have positive curvature, which is supported at finitely many points, exactly as in this case, can actually be realized as a polytope in a tree. Okay, so this is somehow the simplest situation. But there is also a study of the global structures of such polytopes. When you want to change the angles, for example, and then you want to understand how the whole family behaves. There's a nice theorem by Thurston from the end of the 90s, saying that if you fix the angles, then the family of flat metrics with m conical points is actually locally isometric to a complex hyperbolic space, which completes to a stratified set of finite volume. And there is more recent work by, for example, Mazzeo and Chauvin Zhu in the study of more general phenomena of this type. Okay, let me know if there is any question I can answer at any time.
I had a quick question.
Here's a question. Okay,
in the
good.
previous slide, in the Alexandrov result, what do you mean by realized as a polytope?
Yes, so you start from an abstract topological sphere, okay, not embedded in any space. So you start from a two-dimensional surface, abstract, and you require that the curvature as a measure, you require that the curvature is a positive measure supported at finitely many points. Okay, then there is a realization theorem by Alexandrov. It tells you that that abstract surface can actually be realized as a polytope in a tree.
And
it's
realized here
like,
is just a homeomorphism, is it?
It's actually an isometry. So it's a bit like Whitney's or Nash embedding theorem. Okay, so you start from an abstract manifold and you can embed it into a Euclidean space. Here you can embed it with singularities into a Euclidean space with the codimension 1. Okay,
Thank you.
actually in a tree. Yeah, it's a wonderful theorem. So usually you need embedding in a much larger dimension, but here you can make it actually very concrete. It's one of the few cases which is completely understood. Okay, so extending the uniformization question, you can also ask it for conical surfaces, okay, on when you have singular points. Okay, so the goal will be to try to find a metric G tilde with constant curvature on a given surface sigma, but having prescribed conical points P1, Pm, with angles θ1, θm. Okay, so you start from a smooth surface, you fix some reference points P1, Pm, and then you want to deform it so that the new surface becomes like this, so with finitely many conical points, and you want at the same time to have constant Gaussian curvature in the smooth part. Okay, so the singular structure is usually encoded in a divisor, how the algebraic geometers call it. So this divisor is a formal sum of singular points with weights, alpha j. And the standard notation is that this weight, alpha j, measures the discrepancy from the round angle. So the difference of the conical angle from 2 pi. Okay, so for example, if the conical angle is 2 pi, so when the metric is flat, then this discrepancy alpha will be greater than 0. And we want this angle to be positive, so we require alpha to be bigger than -1. Of course, the standard cones have alpha less than 0, so an angle less than 2 pi. But you can, of course, consider angles that are also bigger than 4 pi. Okay, so what kind of curvature do they carry in the distributional sense? Well, if you take a cone, the smooth part can be obtained just by folding a piece of paper. Okay, so this is an isometry because I'm not creating wrinkles on the paper. So on the smooth part, the Gaussian curvature is 0, but at the tip, the Gaussian curvature is a measure exactly as before. So what is the measure in this case? So if the conical angle is 2 pi 1 plus alpha, then the Gaussian curvature here becomes a Dirac mass at the conical tip with weight minus 2 pi alpha. Okay, so if alpha is negative, you get positive curvature here. You can think, for example, of smoothing the tip to some smooth surface, and then the curvature would be positive. But if alpha is greater than 0, then the curvature here becomes negative. So it's all concentrating at the tip, and you don't see anything on the smooth part. Okay, so now if you want to uniformize the surface with conical singularities, you need to solve for a singular Liouville equation. So the operator on the left-hand side is the same as before, but now on the right-hand side, so you have your constant term here, multiplying an exponential term, and you need to add the distributional part of the measure, which is the sum of some Dirac masses with weights, and the weights are minus 2 pi alpha j. So there is still a constraint by the Gauss-Bonnet formula, so which is a singular type. So now the constant curvature here that you get, so for example, if the volume is 1, must be equal to the Euler characteristic multiplied by 2 pi, but then you need to add the 2 pi times the sum of the weights alpha j. So it's a singular Gauss-Bonnet formula. All right, so recall the singular Gauss-Bonnet formula. Now, even this new equation with Dirac deltas on the right-hand side, it admits a variational structure. So to see that, you need to change, make a change of variables. Okay, how do you do that? Okay, so basically you need to subtract. So since here we have Dirac masses on the right-hand side, you would expect the solution to become singular, so to behave logarithmically near these conical points. So after you subtract the logarithms, then it becomes a variational problem. And we have, from the variational point of view, 3 different situations. So there is the so-called subcritical case, when the curvature is sufficiently small. In this case, the energy that you obtain, I don't even write the energy, but it's similar to the one we saw before for the classical uniformization problem. In this case, the energy is coercive, and you can find the solutions as global minima exactly as before. So this was done by Choyanov via a singular Moser-Tuninger inequality, which takes the conical points into account. So some cases were already treated by Picard back to the 1880s. Okay. Now there is a critical case which corresponds in the previous situation to the topological sphere. Okay, in which rho is exactly equal to this quantity. So in this case, the energy is bounded from below, but not coercive. And differently from before, you also find supercritical cases in which the curvature exceeds this quantity here that depends on the angles. So in this case, the energy becomes unbounded from below because the multitudinal inequality does not control anymore the logarithmic term in terms of the Dirichlet energy. And there is no classical counterpart of this situation. Okay. And in fact, in some cases, it's a problem for which you have no solutions. Okay. One classical example is the so-called teardrop. Okay, there's a custom-bounded type of fraction, so you can show that there is no solution via some integration by parts. So a classical example of non-existence of solutions is the teardrop. You consider a topological sphere with a single conical point, okay? And you can show that there is no constant curvature on metric on such an object. On the other hand, there is one prototype singular surface for which you have existence of solutions. It's the lemon or say the North American football. So the South American football would be round. Okay. In this case, it's still a topological sphere, but with two conical points. Okay. And in this case, the integral of the Gaussian curvature by the singular Gauss-Bonnet formula is 4 pi times 1 plus alpha. Okay, so alpha equal to 0 corresponds to the round sphere, but here we have two singular conical points. So how do you obtain such an object? Well, you can start from a sphere, then you cut two meridians and glue together these two sides. Okay, so in this way, you obtain an American football. Okay, so why do you have non-existence in these cases? Because from the PDE point of view, the difficulty involves some blow-up phenomena, as we saw for the Möbius group on S2. So which means indefinite concentration of energy or volume. Okay. But still, sometimes you can hope to find critical points of saddle type. Okay, so let me try to describe this volume concentration. Okay, so we are in the supercritical regime, so when your energy is unbounded from below. So as we saw for the case of the Aubin's inequality, which had to do with the center of mass, it is useful to understand the functions with low energy. And you can show, as it happened for the Möbius group, that when the energy is low, then the volume tends to spike and in a sort of uniform way. So you can describe very well how this volume concentration happens. So let me do it. So the principle is the following. So you look at your energy. If it is low, then the conformal volume concentrates at a finite number of points. And it is possible to describe at how many points this can happen and what is the somehow the character of these points. Would they be the regular points or conical points? Okay, so all of this depends on the topology of the surface and on the structure of the divisor, so of the conical points and conical angles. Okay, somehow this energy behaves a bit like an engine. Okay, so let me try to describe this concentration phenomenon. So I introduce a weighted cardinality on regular and singular points, depending on their character. Okay, so I weight 4 pi regular points. Okay, and if instead you have a singular point with conical angle, so theta equal to 2 pi 1 plus alpha, then I say that the weight is 4 pi 1 plus alpha. And then I extend this counting to finite sets by additivity. So I take any finite set on the surface. It will be union of regular points and singular points, and I count them one by one with this weighted counting. Okay, so my claim is the following, that if the energy gets low, then the possible concentration measures are the ones that are supported on finite sets, so that the weighted counting is less than rho. So rho is the curvature which is given by the singular Gauss-Bonnet formula. Okay, so what can you say about this set of possible concentrations? So these are measures, okay? They will be formal sums of Dirac masses, okay? Because you only have a concentration of finite points. Okay, so this is in general a finite dimensional set, but a non-smooth set. So it will be a stratified set. And the point is that when you have this measure supported and more than one point, it's no more a good parametrization. So you expect some sort of strata in the description of this set. So you might obtain an object which is of this kind. You can imagine a surface, two-dimensional, smooth, but with a one-dimensional handle attached. Okay, you obtain objects of this kind. And we have the following theorem joined with Carlotto. Okay, so suppose that rho is generic, so it avoids some explicit discrete set in R. This is for compactness reasons. And assume that this stratified set, which I defined before, is not contractible. Okay, so it's something like this. Then the Liouville equation is actually solvable. So the singular Liouville equation. So as I said, this condition, I don't even write the explicit form of lambda alpha bar. So it's a discrete set in R. So this is used for compactness reasons. Okay, so to be able to use the variational tools, Mohs theory, min-max theory. So for example, if you consider a saddle, so the classical saddle in R2, what you observe is that when you cross the energy level, there is a change in the topology of the levels. Okay, and we have an assumption which more or less matches with this one for the simple case of a saddle. And the case of rho belonging to this discrete set would require a sort of singular counterpart in Minding's theorem. So the rigidity of flat metrics on simply connected sets. Okay, so for the T-drop, we saw that there are no solutions. So when you take a topological sphere with one singular point, and for that case, the set of measures which occurs in this theorem will be either a point or the sphere with a point removed. So it will be a contractible set. And that's why you cannot apply the above theorem. So it will be also interesting to obtain in general other non-existence results. And there is some work by Carlotto from 2014. So he takes conical angles with a very sharp tip and show that even for positive genus, you might have non-existence. Okay, let me mention that there are other results using monodromy theory. So by Luo Tian, Ling Wang, and more recent contributions by Li Xu, Ermenko, Mondello, and Panov. So they use completely different techniques. Okay, so how can you characterize low energy levels as I claimed before? So why does this concentration happen? Okay, so the claim or the argument was the following. So suppose that you have very low energy, okay, and therefore, the volume is closer to one of these meshes distribution. Okay, so in general, you can improve the Moser-Tudinger inequality if you have the exponential function, which is macroscopically spread over the surface. So this is a bit in the spirit of Aubin's improved inequality, which requires the balancing condition of the volume. Okay, if you have the volume which is all concentrated near a single point, that would be very unbalanced. Okay, in general, the more you spread the volume of a surface, the more the Moser-Tudinger inequality improves. Okay, and then you argue as follows. So if you have a spreading of the volume, you improve in a Moser-Tudinger inequality, and that helps you to get lower bounds on the energy. So therefore, if lower bounds fail, you just go back in the sort of reverse implications. It means that the Moser-Tudinger inequality was not improving, which implies concentration of volume. Okay, so I would like to describe briefly some new improved Moser-Tudinger inequality via angular moments. And I consider a very simple situation, just to get the idea. So instead of taking a closed surface, I just take the unit disk in R2 with one singularity at the origin with positive weight alpha. Okay, so then the catch is that you can improve the Moser-Tudinger inequality, not only assuming the macroscopic spreading of the volume, but also via the angular distribution of the volume. Okay, here's the proposition, so which is proved in two joint works with Ruiz and Bartolucci. So you fix your positive weight alpha and the small epsilon, which you can imagine to be 0, okay, for simplicity. Okay, now you take functions which are in W1 to 0, so they are in class W12 and vanish at the boundary of the disk. And you assume that this volume measure, so there has to be this power of x by the change of variables that I described before. So, but you can think of the conformal volume. Okay, so if you have enough vanishing of angular moments, then you improve the Moser-Tudinger inequality in this way. So the classical Moser-Tudinger inequality is 1 over 4 pi. With a conical point, it would be 1 over 4 pi if alpha is positive. Okay, but here you can show that the more vanishing moments you have, the more this this inequality improves. And eventually you have to stop when k, so the number of vanishing moments, is more or less of order alpha. Okay, as I said, you have this weight from a change of variables that I had to introduce before. Okay, so let me give some comments on this improved inequality. So the main new feature compared to the previous ones, the one by Aubin, for example, is that the assumptions are scaling invariant on U. Okay, so we're assuming vanishing of the angular moments of a measure. And the point is that this volume measure can be as concentrated as you want. So you are actually looking at somehow not the macroscopic structure of the measure, but rather the microscopic structure of the measure. Okay, so you need to somehow unfold it angularly to see some improvement. Okay, another comment is that when you consider radial functions, the best constant is known to be 1 over 4 pi 1 plus alpha. Okay, and therefore you cannot hope to improve the inequality by vanishing of the angular moments. So that's why you see always the minimum between 1 plus alpha and 1 plus k. So there's no hope of exceeding 4 pi times 1 plus alpha, because that's already the best constant for radial functions. And there is also now a matching between the analytic constant, which is 1 over 4 pi 1 plus alpha, and the geometric constant, which appears in the Gauss-Bonnet formula. So recall that when you integrate the Gaussian curvature over an American football, you get 4 pi times 1 plus alpha. Okay, and this constant 4 pi 1 plus alpha we see now also analytically in the improved Moser-Tudinger inequality. Okay, and how do we use such an inequality? Okay, well, it's used to somehow tear apart some ambiguous volume distribution, because suppose that we have a volume distribution more or less like this. Well, you don't know whether to regard it as volume concentrated maybe at the singular point here. Suppose the point C is singular. So you would like to understand whether it's rather a measure which is concentrated at the singular point, or maybe at more regular points which are around the singular point. So it helps to give a sort of interpretation of the highly concentrated volume measure. Okay, so let me now conclude with some perspectives. Okay, I said that when you consider regular polytopes, for example, a cube, okay, so in this case, locally, this is an isometry to a sector of a plane. And therefore, if you have a straight edge, so the edges do not carry any Gaussian curvature. But that is not the case when you have a curved wedge. Okay, so for example, you can think of considering two spherical caps and joining them together. Okay, so this will be still a topological sphere, but the Gaussian curvature on the two caps doesn't match 4 pi, which is given by the Gauss-Bonnet formula. Therefore, it means that the curved wedge must actually carry some measure type Gaussian curvature. Okay, and as far as I know, this is a problem which has never been studied. Okay, so trying to prescribe a measure Gaussian curvature with also part of the curvature which is concentrated on one-dimensional sets. So I think that would be an interesting direction. Going to higher dimensions, so I mentioned the Q curvature problem, but there is yet another variant, so which is that of the singular Yamabe problem. So now you want to prescribe a constant scalar curvature on a manifold of dimension greater or equal to 3, and you can imagine the presence of some singularities, and there is in fact some work in this direction. Okay. So one feature of the singular Yamabe problem is that as for the singular uniformization problem, there are situations in which you have non-existence of solutions. So the regular Yamabe problem, so trying to find a conformal metric with constant scalar curvature on a manifold, so that is always solvable due to fundamental contributions by Tudinger, Aubin, and Schoen. But rather recently, Biaklowski proved that there are classes of manifolds singular with orbifold points for which the Yamabe problem is not solvable. So they will be similar somehow to the teardrop case. So another direction is that of surfaces with boundary. And the natural boundary datum now is involves prescribing the geodesic curvature of the boundary via conformal metric, in addition to the Gaussian curvature in the interior. So this was studied in the 80s by Chaillet, a student of Aubin. And if you want to prescribe the function k of x as the Gaussian curvature in the interior, and the function h of x as the geodesic curvature at the boundary, then you need to solve the Liouville equation we saw before in the interior, but with a nonlinear boundary condition of exponential type. So here the factor, the exponential factor, is 1/2 of the one that you have in the interior. And this is also of critical type. So you have similar phenomena involving loss of compactness. Okay, so if one of the two functions h of k is 0, then we are in a situation which is similar to the previous one, okay? But things change substantially when, for example, the two curvatures have opposite sides. So a model case is that of geodesic poles in the hyperbolic plane. Okay, so in this case, the interior Gaussian curvature is just inherited from the hyperbolic plane. It will be negative. And you have different kinds of balls. So you have geodesic balls where the boundary curvature, so the geodesic curvature, is positive and sufficiently large. But you also have these horospheres, so which are balls that touch somehow the boundary of the hyperbolic space at infinity. They're non-compact, and for which the geodesic curvature is equal to 1. Okay, it's a sort of limiting value, and depending on the ratio of the functions k and h, you might get blow-ups of infinite volume. For example, with the profile of a horosphere. And these are particularly challenging to treat analytically because they will give you infinite volume and infinite Dirichlet energy. So it's a situation that we started to study only recently in a joint work with Lopez Soriano and Ruiz, and there are several open problems also in this direction. So I conclude here and thank you for the attention.
Let's thank Andrea for his wonderful talk. I open the floor for questions.
Thank you, Andrea, for a nice talk. So I have one question related to your work with Carlotto. So you mentioned, you mentioned that, okay, so for rho not in that critical set, lambda alpha bar, you have solution. So what happens when rho approaches to those critical values? So there must be a blow up always, or it depends on something.
That's exactly when you can expect a blow up of solutions. In general, that might happen, and you can see the effect of, for example, the degree counting of solutions. And in general, you do expect a difference in the topology of sublevels. So in that case, one should, in principle, argue as Ding did with Minding's theorem. So there might be maybe some geometric insights that tells you that, for example, blow up might happen only on one side. So maybe you're interested in some of these discrete values. So this is what I call the lambda rho alpha bar.
Yes.
And you might consider rho approaching this lambda on one of the two sides. Yeah. So it could be that in the picture of solutions, maybe solutions are unbounded on the right, but stay bounded on the left. So this has been done for regular Liouville equations by Chen and Lin, but not for the conical case. So it would be interesting to have any argument in this respect.
Okay, thank you.
There is, as I said, some approach via complex analysis, meromorphic functions, but they mostly deal with the spherical surfaces. So the progress with surfaces of positive genus is extremely limited.
Okay, thank you.
Are there other questions?
I have one question. So the theorem appears with Carlotto. So the So it's not a both-way implication, right? Meaning that if your set is not contractible, you won't have any like existence or non-existence.
Right.
And how do you use that to get some like information on distribution finally?
Information, sorry, on
the how do you like use that to get the existence result finally?
Oh, right. Yes. Because it turns out that okay, let me draw a picture. You can show that somehow you look at the topology. So you have an energy which I call J, and then I look at maybe let me do this. So I have an energy which I call J, and then I look at the structure of the topological levels or the sublevels of J. So J less or equal than B. Okay, for B in R. So typically, when the topology of this set changes, it's a sign of the presence of a critical point. Okay, so what we do is to consider two cases. So one, B close to plus infinity. And in this case, you can show that the sublevel is topologically trivial, is contractible. Second, when B is close to minus infinity, okay, then this set inherits the topology, so it's topologically richer than sigma rho alpha bar, so the set of measures. Okay, so if this set is non-contractible, it means that this set is also non-contractible, and therefore you obtain two levels, one close to plus infinity and one close to minus infinity, for which you detect a change in topology. And then you argue pretty much as for the saddle. So when you consider fxy in the plane, just like x squared minus y squared. Okay, so you look at the levels f less or equal than plus epsilon. This is a connected set. And f less or equal than something like this. F less or equal than minus epsilon. This is a disconnected set. Okay, so there is a change in topology. And if you have compactness conditions, it's a sign of the presence of critical points. So we use this assumption to detect a change in topology from very high sublevels of the energy and very low sublevels of the energy.
So I think the difficulty would be to avoid those points where the concentration might happen, the energy levels.
Exactly. That's why we assume that rho does not belong to this discrete set lambda rho alpha. Okay, these are, I can tell you what it is. So it's a set of numbers that are sums, and maybe let me, okay, so this discrete set lambda rho alpha bar is the sum of, so actually depends only on alpha bar, sorry, is the sum of numbers. So of the type k for pi plus sum over some subset I of for pi 1 plus alpha j. So for pj belonging to any finite set I. So I finite set. Okay, so you can show that when a volume concentrates, it can either concentrate at regular points, so forming a bunch, a sort of bouquet of spheres. So you get k spheres. And so plus some other American footballs. So plus, say, L American footballs. And you can show that all the volume goes into the spheres or the American footballs. So therefore, if you blow up, the volume is quantized as the sum of volumes of spheres and the sum of volumes of American footballs. So if you avoid this discrete set of numbers, then blow up cannot occur, and then you can run your topological methods.
Okay, avoiding those methods. Thank you. I have one last question, something more heuristic.
Yes.
For the fourth order Liouville equation, for the second order case, there is this very nice interpretation of the singular curvature. So for the fourth order, is there some like geometric or physical interpretation?
Oh yeah, yes, yes. You can also, there is actually some recent study of that. And you can actually have also a similar interpretation, because in 4 dimensions, there is a Gauss-Bonnet formula. So in 4 dimensions, you have that, so the Gauss-Bonnet, the Chern Gauss-Bonnet theorem tells you that the Euler characteristic times 4 pi squared is equal to the integral over the manifold of the Q curvature plus the Weil tensor squared over 8. So in 2D, you only have the Gaussian curvature, but in 4 dimensions, you need to take into account also the Weil tensor. So if you consider conical points, then you might have a similar interpretation. So the conical point would carry an amount of, say, suppose that the value is 0, then in this case, the conical point would carry some amount of Q curvature. So you can think again of if you start from a conical point, you can round it off. So compute your curvature for the smooth metric and then pass to the limit. So there is a totally similar interpretation, but in 4D, you also need to take into account of the Weil tensor that you don't see in 2 dimensions.
So there is this part of this smoothing part, and then there's a regular part, 2 parts.
Sorry, I did not.
So there are similarly 2 parts. One is a singular part, which one can approximate by smoothing, and then the regular part.
Exactly. Yes.
Thank you. Thank you so much. Thank you for the very interesting talk.
Thank you.
Are there other questions from the audience? Okay, let's thank Professor Andrea Malchiodi again for the wonderful talk and the interaction which followed.
Thank you
Very much.